which aren't. This is the test data set, which we also need to scale because we'll be testing it as well later. But we want to keep them very separate. So this is now your test data set. Okay. So now let's take a look. We're going to actually plot some things. So we import matplotlib and some other statistical functions here using Seaborn. And this is just looking at both our malignance, which is 1. Remember, malignant was 1 and benign was 0. Looks like we have this is a number there, it's 0.4 and 0.6. So although they're not equal, it's relatively well balanced. If this was only maybe 1% or 5% of malignant cells, you'll find that you're not going to do a very good job at training. Basically, the machine learning program is going to basically figure out, your classifier is going to say, well, you trained me and basically said that everything is basically benign and there is no malignancy. I'm just going to guess that it's benign. The algorithms always will take a shortcut. So in order to prevent the shortcutting, you need to have a fairly balanced data set, which we have already here. Let's take a look at some of these features. Let's look at the perimeter mean, just to kind of get a sense. So it's nice distribution. It's going from 0 to 1, and this is sort of the shape of that feature. Okay. You can also look at correlations. This is a little bit, well, actually, well, very busy slide, but basically using the correlation function, and you can see that, well, the one that makes the most sense is that diagnosis should be correlated to. So we can get this up here so you can see both. You can't, but basically this is diagnosis against diagnosis. This is symmetry mean against, let's put it here, good. So symmetry mean against symmetry mean, that should be perfectly correlated. It just gives you an idea of which features are better correlated with other features. And so high number means high correlation, low number means low correlation. It also may turn out that some numbers are really probably too related to each other, so you really actually don't want to be using them. So if you think about it, radius mean and area mean, they're probably related, and perimeter mean. So it's like 0.74, 0.71, and 0.73. It's not clear whether you want to have all those features in it. It might actually hurt your algorithm, but that's part of the magic that goes involved in actually creating these algorithms. You need to choose them. So let's just make this, and let's pin this down to a much smaller set just to get a better feel for what's going on. So we're just going to use radius mean, perimeter mean, compactness mean, and concavity mean. Okay, those 4. And we can look at, here's radius mean. I'll take a look at, has a correlation of 0.73, perimeter mean is 0.47. The other two, compactness mean and concavity mean. So compactness is here, it's a 0.6 and a 0.7. So they're somewhat correlated, but let's see how they do. And you could choose any one of these. I really recommend playing with this, using just 1, 2, 3, and then trying to use your classifier and see how it works. So we ran the correlation, and now we're going to run the prediction. Actually, we're going to set the prediction variables. Now we're going to train our model. Okay. And this is going to be our training set, is going to have, there's going to be a training X and a training Y. There's going to be a test X and test Y. The test Y and the train Y are basically the predictions. That's the thing we want to figure out. So now let's load up a classifier. This is basically a standard neural network. And we're just going to give it a couple of features here, 5 and 2. 5 and 2 essentially is the number of layers. And you can go online and kind of learn about this, and it's really straightforward. But the idea is being that this is going to be a fairly simple neural network where there's going to be a hidden layer with 5 neurons and a second hidden layer with 2 neurons. So there'll be an input layer, which are the features. There'll be a hidden layer of 5 neurons, another hidden layer of 2 neurons, and then the predictions. And what we're doing here is we're going to, with this, I'll run it again, doesn't really change anything. This basically takes as input the training data set, train X and train Y. It uses this neural network and it creates the classifier. So model is the classifier. That's where all the weights are. So that is your model. We can actually do that for a number of different classifiers. When we went for logistic regression, and we're going to have model LR. That's going to be the model using logistic regression. There'll be another model using random forest classifier. Here's one for k nearest neighbors, and here's one for support vector machines. At this time, I wouldn't really, don't worry you don't know all these different things, or maybe you're an expert at them, but just think of them as different algorithms that you feed a series of features, and then they give you what they think it is. So imagine for support vector machine, the way that's working is you have a slide, you look at the slide, the computer then decides all these different feature sizes that we're going to be using in this case, which are here: radius mean, perimeter mean, compactness mean, concavity mean. We put them into this model, and then we predict what's coming out. But we've actually trained the model, so all you need to do is just put in the features, and an answer comes out by magic. So if we run this, these are the predictions. So if you take, now we've already done the training, so now what happens when you act on the test set? So this is, now if you take the model, or model, these are all the 5 different models, and you use the predict feature. If you put in the inputs of the test data set, you'll be able to predict what's coming out. All right, so I know I've talked about a lot of things, so it does get pretty confusing. It's actually much better if you do it. You got to do it yourself to really feel it, and I really would recommend playing with this code and actually making a video yourself. So you really kind of, if you can teach yourself how to do this, you actually can understand what's going on. And that's all I'm hoping that you guys get out of this. So what is this test set? Remember, this is the test set. It was 114 by 4. This is basically all the different radiuses, perimeters of the different slides. This is a slide, and this is the radius of all the cells in that slide on average, the perimeter, their compactness and concavity of the cells on that slide. And these are all the different slides, and we're going to try to see if we can predict whether benign or malignant. The good thing is we actually know the answers, but we're going to try to predict it first. And we're going to use support vector machines. I'm not going to tell you yet, but it actually turns out that a little secret that this one actually does the best. So we're going to click this one, and these are all the predictions. So for this 0 slide, the prediction is that this is a malignant side. This is malignant. This is malignant. The 4th one is benign, no cancer. All right. So let's actually run that again, and then let's see how good did it do. So Y are the actual member tests. Those are the answers. So let's look at the answers. The first 1 and 1. Oh, that's pretty good. We said it was cancerous. It is cancerous. We said it was cancerous. It is cancerous. We said it was cancerous. It isn't cancerous. The 4th one, we said it's not cancerous. Not. So actually, it's doing pretty darn good. All right, that's a support vector machine. Okay. We can calculate these things. Now, I'm not going to go in detail all these things like F1 score, but really, you should have learned that already in a course, or you can go online and learn about it. But we're going to calculate the F1 score. Basically, the higher the F1 score, the better. The actual, I'm getting here 0. Kind of depends on when you run it. Every single time is a little bit different. But yeah, in this case, the F1 score is 0. You'd like to have it as high as possible. Looks like the regression is actually doing pretty good this time, and support vector machine is really 0.8. Now, for me, I'm not supposed to a F1 score. I actually like to use, actually area in the curve is what I use the most, and sensitivity and specificity, but a high area in the curve is what I like to see and decide to use. This one has area in the curve 0.6. That's for just the regular neural network classifier. Now you can always make that better by using different features or choosing different number of layers. You probably can play with that and make that much better, but this is what we're getting right now. Logistic regression has an accuracy of 0.92, but its area in the curve is really 0.5. Now, when you learn about area in the curve, basically 0.5 area in the curve is the same as flipping a coin. So anything near 0.5 is basically horrible. You need to have it up around 0.8, 0.9 is actually really pretty good. Of these, looks like the k nearest neighbors and the support vector machine are actually the AOC is a little bit better on this one, 0.91 and 0.9. Just kind of, since I'm sort of telling you that the MLPC is actually pretty terrible, let's try this live and see what happens. I actually want to see what these predictions are. So remember, for the standard neural network classifier, that's just the predictions. Let's see how that does. Look, these are all 0. So it's pretty terrible. It's actually pretty 0 the whole time. So maybe there's some mistake there, but whatever it is, it's not doing very good. The k nearest neighbors looked like it was doing pretty good, right? So that one is kn. Let's try that. Shift kn. Let's see what happens. How are those predictions looking? That's actually looking a lot better, right? So this is the actual answers. 1110, getting 1110. That's actually pretty darn good. And if you look at, well, I'm not going to count them out, but it's definitely doing better, which is what we were expecting here. And so I don't. The F1 score is actually 0.88 for the k nearest neighbors. I'm going to set this up for the support vector machine, which is the one I like the best, at least that time. So what was called is SVM predictions. And those are those predictions.